Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. How's everybody doing today? So we're just at the end of week 5, so I know midterms are starting up very soon for a lot of you guys. Great, good. Yeah, so our midterm is in 2 weeks, so it's not going to be next week, it's going to be the week after next. So, we have one more lecture notes to complete on frame equations. And then next week, we're actually going to do an activity and to see, how do we implement these guys in Matlab. And so I want to have the midterm after those things. Okay. So we'll talk about the midterm more next week, but just to give you guys just a little bit of a heads up, I've been thinking a lot this semester on how to do midterms, and I know every faculty is doing something a little bit different, but I think what I ultimately ended up deciding, I think especially for you guys, where you guys are graduate students and you guys have a lot of else going on. So I know a lot of you guys are working on research and teaching and all that stuff. So I wanted to give you guys as much flexibility as possible. So what I decided to do is I'm going to have a 24-hour exam for the midterm. And so what that means is that on the exam date during the class, at the class time, I'm going to publish an exam onto Canvas. And so I'm going to use basically their built-in quiz feature in there. And then you'll have 24 hours of real-life clock time. So whether you're logged into the quiz or not, 24 hours to complete the quiz and then upload your solutions back onto Canvas. So basically the quiz is going to take place starting Wednesday 5:30 until Thursday 5:30. Okay. All right, so the question is, how many questions are going to be on the midterm? So the midterm is going to be 4 questions. So question 1 is going to be a short answer question, so very similar to the short answers you've been seeing on the homeworks. Or I guess actually, we haven't had that many homeworks yet. I'm working on one more homework for you guys to do. And so basically what that first question is going to test is just your conceptual understanding. So those will be questions that you can answer in like 2, 3, 4 sentences. And then every question after that will be, there will be 3 more questions after that, and those will be kind of hand calculation problems. So I know next Wednesday we're going to do like a MATLAB activity, but the MATLAB stuff won't be on the exams. The exam will just be testing you on how you can set up the problems by hand, and then that's been setting up the matrices, assembling, applying boundary conditions. So by the time we reach the exam, we'll cover 3 big units, which is direct stiffness, trusses, beams, and also frame elements. So those are going to be the subjects for the exam. We'll talk more about it next week, but I just want to give you guys a heads up just to see that it's coming up soon and just what you can expect for the format. Yeah, sure. What's up?
So the way you're doing the midterm, right? Would it be heavily on MATLAB, or would it be more hand calculation based? Because I'm trying to relate that to the comprehensive exam that I'm taking in the future.
Yeah. So so this midterm exam will just be hand calculation based, so there will be no MATLAB. And so the way I'm going to test you guys on the MATLAB is going to be on the final project, because the final project is I'm going to have you guys implement a fairly sophisticated finite element code. But for the midterms, I want those to kind of model, what you would face on like the comprehensive exam, because I know a lot of you guys are planning to take that. So for the comprehensive exam, you're not going to be able to have MATLAB, so it's going to be just the hand calculations on the midterm. So very similar to what you would see on the comprehensive.
Okay, great, thank you.
Yep. Mm-hmm. Okay, so that's the exam. So that's in 2 weeks. So that's not next week, but the week after that. So next week, I think I'll have more details for you. I'll have one more homework assignment for you guys to do next week too, and then we'll go from there. Okay. Okay. So the plan for today is we're going to we had just a very small amount at the end of last lecture, so it was too much to do in the last 30 seconds, but not in, it probably only take us just a couple minutes to do today. And then we're going to move on to our next set of lecture notes on frame equations. So kind of the last big lecture notes for this kind of unit on the direct stiffness method. Okay. So there's a question in chat. So will there be a review session? So we're not going to have time to do a review session in the class. What I've been doing for my other classes is I'm going to pre-record a review session where I'm going to basically review everything for about an hour, 15 minutes for the exam. And then I'll post that onto Canvas for you guys to view kind of at your own leisure. So just because, there's a lot of stuff that I want to cover in this class with the Matlab and the ANSYS stuff, we're not going to have enough time to do it in class, but I do want to make sure that you guys have something to review for the exam. Yeah. Mm-hmm. Yeah, so I'll probably do that sometime middle of next week, and then I'll have it posted there. So usually what I do for my review sessions too is I put a poll onto the class website, so you guys can vote on what topics you want to see the most. Because I think it's more useful to cover like 2 or 3 topics in pretty decent detail, the ones that people are kind of struggling the most with, rather than just having like a smorgasbord of everything, and we only cover everything at a surface level. So so I'll put a poll out next week so you guys can vote on what topics you want to see the most. Okay. All right. Are there any questions on that, or the just anything we covered last time, or anything about the class that I can answer before we get started? Okay. So let's go ahead and finish up where we left off last week. And so remember where we left off, or last Monday. So where we left off on Monday was how do we take a distributed mode and convert that into a nodal mode? Okay. Right, so just a reminder, the way that we did that was that we took the distributed mode and we used the principle of equivalent work in order to equate the work done by the distributed mode and the work done by the equivalent nodal mode. So I think where we left off was we were at this point where we plugged in our assumed function of our displacement function, and we were solving for the coefficients for each of the terms. Okay, and so let me just write out where we left off. So we were at an expression that looked like this. So we had 5,000. So 5,000 in this example was from the loading function wx, and then we had 2/5 u1y minus 2/5 u2y plus 1/5 theta 1 plus 1/5 theta 2. Okay, and so remember these are for beam equations. So these are all the deformations that we expect from a beam. Okay, minus 3/4 u1y plus 3/4 u2y minus 1/2 theta 1 plus 1/4 theta 2. Okay, plus 1/3 theta 1, and then plus 1/2 theta or u1y. Okay, and so this is the expression that we had at the end of lecture last time. And so what I was saying before we left was that what we're going to do is we're going to take all the terms that have the same nodal value. So in this case, all the u1y's. Okay, and then we're going to take all the u2y's, and then we're going to group those together. Then we're going to take all the theta 1's, and then all of the theta 2's. Okay? And so what we want in the end are coefficients for each of these guys. Okay? And so, oh, question. Minus 1/4. Yes, thank you. I think I made that same mistake last time too. Okay, and so let's go ahead and write that out. And so let's group all the terms basically. Okay, so we have 5,000, and then we have the u1y terms. So 2/5 minus 3/4, and then plus 1/2. Okay, this is all u1y. And so those are basically all the coefficients you see up there. Next, let's do u2y. So we have a minus 2/5, a plus 3/4. Okay, this is u2y. Okay. Next, we have theta 1. So theta 1, we have 1/5 minus 1/2 plus 1/3. Okay, and this is theta 1. Okay, and then we have theta 2, which is a let's see, 1/5 minus 1/4 theta 2. Okay, let me see, double check. Minus 1/2. Yep. Okay. And so what we do, all we need to do here is just perform this arithmetic, and then we'll get all the coefficients for these guys. Okay. All right, any questions on this? Question? So the question is, probably better to leave these as fractions because of the floating point operations. Yeah, so in this case, you know, it is leaving it in fractions is a little bit more convenient. It also saves you a little bit of writing and looks a bit cleaner too. But in reality, you know, sometimes, you know, you're going to do these in the computer too, so the computer will do these as decimal. So you can do whichever one that you want, but for this particular problem, you know, since we went through the trouble of saving all the fractions here, I'm going to express the solution in terms of fractions. Okay, and so let's perform that arithmetic. And so we do that, and then we multiply by 5,000, and we get the following. So we get 750 U1Y plus 1750 U2Y plus our only irrational guy. So we have 500 over 3, theta 1, plus 2,250 theta 2. Okay. And so now what we're going to do is we're going to equate this to the work done by the nodal forces. So this is work discrete. Okay. And so remember, this is equal to F1y U1y plus F2y U2y plus M1 theta 1 plus M2 theta 2. Okay. And so from here, what we can do is we can just equate the coefficients. So we have 750, that's going to be equal to F1y. Okay. Then we have 1750, and that's going to be equal to F2y. We have 500 over 3, that's going to be M1. And then we have 2,250, and that's going to be M2. Right? And so we can write out our final answer of F1y. This is equal to 750 newtons. Okay. F2y is 1750 newtons. Okay. Then we have M1. This is 500 over 3 newtons meters. Okay. And then we have M2 is 2,250 newtons meters. All right. And so that's basically the end of that example of how you transform a distributed loading and then you turn it into nodal loads. Okay. All right, any questions on this example here? Okay. So when you have distributed loading, you know, it's quite a bit of algebra and a lot of work, but you know, it's hopefully it's not too bad. It's just you just have to kind of be careful with your arithmetic and make sure you carry all the signs correct. Okay. And so from there, let's move on to the next topic, which is frame equations. Okay. So frames kind of represent the last element type that we're going to cover here in the direct stiffness method. Okay. And so let's kind of summarize just everything that we've done so far. And we'll categorize that in terms of the types of deformations that they allow. Okay. So the first one that we did was springs. Okay. And you know, because they deform in the same way, we'll categorize them together with trusses. Okay. And these guys were similar in that the way that they deformed was purely axially. So only you know, you can only compress them and you can only expand them. Okay. And so the unit that we just finished is on beams. And so beams are unique because they can do both transverse deformation and rotation. Okay. Okay, and so you know what this means is that you know if you want to use this direct stiffness method to analyze some kind of structure, you know you have to kind of make a prediction beforehand about how you think those structural elements are going to deform. And so if it's going to be a system where you only expect the elements to compress and elongate, you can model it as a truss. But if you see that the beams or the structural elements are going to be loaded transversely and there's going to be a lot of bending, then you might select a beam for that. Okay. But as you know, in reality, a lot of times it's not that simple. So a lot of times you'll have a structural element where you expect all kinds of deformation. So axial deformation, transverse deformation, and rotation. And so in those cases, it's going to be hard to choose whether you want to do a spring or a truss, or if you want to do a beam. Okay? But in these cases, which are complex and you can't choose, you can ask that one cute little girl from that mobile commercial a long time ago. So why not both? Okay. Because real structural elements can deform in all these different ways, and so why don't we just design an element that can do all these kinds of deformations? Okay, and that's exactly what a frame is. Okay, so frames can exhibit all these different types of deformation. Okay. Okay. And so the way that we're going to progress through this unit is exactly the same as what we did for the previous ones. Is first we're going to develop the element stiffness matrix, and then once we have the element stiffness matrix, then we can start to use it in problems. Okay? And so the only thing that's really different between all the different types of elements that we've been going so far is just the element stiffness matrix. But once you have the element stiffness matrix, the way you go about assembling is always the same, and the way you go about assigning boundary conditions is the same, and the way that you end up solving is the same too. And so the first thing we're going to do is we're going to get the element stiffness matrix. And along the way, actually, we'll also find the element stiffness matrix for a beam in the stationary coordinates, because actually everything that we've been doing for beams up till now have just been in the local coordinates of the beam. Okay. All right, any questions on this so far? Okay. Okay, so first let's do that. So let's find the beam element stiffness matrix in the stationary coordinates. Okay. Okay. And so if you recall from from the week that we did truss elements, the way that we transformed from the local coordinates to the stationary ones was we had to apply our transformation matrix. Okay? And so our relationship looks something like this. Okay? And so on the left right here, we have the deformations in the local coordinates. Okay? And so here we're just considering x and y, so there's no rotations. And then the way that we related this to the stationary deformations was that we multiplied by a matrix here. Okay. And so our transformation matrix was cosine, sine, minus sine, cosine. Okay. Okay. And so all we have to do in order to get the beam elements is to, first of all, we have to expand this transformation matrix in order to account for the fact that our beam has two nodes and it has rotations. Okay. So let me just label this first. Okay. And so for beams, it would look something like this. Okay. And so, first of all, even though our beams only have a a transverse displacement and rotation, we're going to expand this to in order to include everything. Okay? So we're going to have u1x hat, u1y hat. Okay? And so we're also going to include the rotations. So we're going to have theta 1. Okay? Right? And then the same things for the node 2. So we have u2x hat, u2y hat, and theta 2 hat. Okay. And so if we expand this transformation matrix, we can get the transformation. Okay. And so this is going to be cosine, sine, minus sine, cosine. Okay. And so that's our transformation matrix. Okay. And so that's how we're going to transform the ux and uy. Okay. And so the question now is, how do we actually transform the rotations? Because the rotations here don't show up in our transformation matrix. And so we're actually in luck. So the rotations, because they don't have any units, we actually don't need to transform them at all. We can just put the same values over like that. Okay. And so since rotations are given in terms of radians, which isn't technically a real unit, you know, we don't actually have to do anything. So we don't have to multiply by sine or cosine. And so we can just have a 1 right here. Okay? Okay. And so that's the kind of the transformation quadrant here for node 1. Okay. And then we can get the same, and then we're just going to input the same thing in here for node 2. So we have cosine sine 0, minus sine cosine 0, and then 0, 0, 1. Okay. And so here's kind of the transformation quadrant for node number 2. Okay. And then this is going to be equal to the analogous things in the stationary coordinates. Okay. And so we can use this transformation matrix along with you know, with the local deformations in order to get the deformations in the stationary coordinates. Okay. Okay. Any questions on this? Okay. And so now that we have our transformation matrix that accounts for the rotations, all we got to do is just multiply this both before and after our element stiffness. So in order to get the element stiffness in the stationary coordinates, we're going to take K, where K hat here is the element stiffness matrix for a beam, which we covered, you know, in the last week. Okay. And then we're going to pre-multiply by our transformation matrix transposed. And then we're also going to post-multiply by that as well. So same process that we did for trusses, except now our K is different. And so if we evaluate this, we get the following. Okay, so we still have an EI over L cubed out in front. Okay. Then we're going to have a 12 sine squared minus 12 sine cosine. Okay. Minus 6 L sine minus 12 sine squared. Actually, let me rewrite this so I have more room. Sorry, everybody. So it'd be 12 sine squared minus 12 sine cosine minus 6L times sine minus 12 sine squared, 12 sine cosine, and then minus 6LS. Okay, so that's the first row. Next row, we're going to start over here. So we have 12 cosine squared, 6L cosine, 12 sine cosine, okay, minus 12 cosine squared, 6L cosine, okay, 4L squared, 6L sine, minus 6L cosine, and 2L squared. Okay. We have 12 sine squared, minus 12 sine cosine, 6L sine, okay. Then 12 cosine squared minus 6L cosine, and then 4L squared. Okay. And of course, this is symmetric. Okay. Right. So a much neater version is in the notes. So I would look at that one more than this. But you can see that this is starting to get pretty big. So you can see now we have an element stiffness matrix that's 6 by 6, which I think is bigger than anything that we've had before. So you know, the addition of the rotations that the beam introduces really you know, complicates things quite a bit, and it makes our element stiffness really huge. Okay. And so this is our element stiffness matrix. For a beam in the stationary coordinates. Okay. All right. Any questions on this? Okay. Okay. And so so that's the you know, stationary coordinates for the beam, but we're not really interested in beams anymore. So we want to move on to frames. Okay. And so remember, frames combine both the axial deformation of a truss together with the transverse and the rotation of a beam. Okay. Okay. And so, you know, that kind of begs the question of, you know, how are we going to form this element stiffness matrix? Okay. Well, we actually don't have to do that much because we already have an element stiffness matrix for a truss, and we already have an element stiffness matrix for the beam. We can just, why don't we just kind of combine the two into one? Okay. Okay. And so let's do this first in the local coordinates. Okay. And so let's define two variables just to make things easier. Hopefully help me fit it all in one line. Okay. And so let's define C1 to be our, if you remember this, this is kind of like our spring constant for a truss. So it's the cross-sectional area of the element times the Young's modulus divided by the length. Okay. Oh, question. So so question is, for multi-axial deformation, we have to have rotation not be dependent. So yeah, that's true. So if you have a three-dimensional problem where the rotation, you can rotate both in and out of the plane, then there's going to be some dependencies there. But we're just considering 2D problems, so the rotation is assumed to be independent. And we also make that assumption that the rotation is dependent because we assume kind of relatively small rotations. We can relate it to the transverse deformation by the derivative. So I think that's also kind of helping us keep it independent from each other. Yeah. Okay. And so we can define another constant C2. And so this will be EI all over L cubed. Okay. And so if we just straight up combine these guys together, then we get the following matrix. Okay. Okay. So we have C1, and let me go down the column first. So C1, 0, 0, minus C1, 0, 0. Okay. Then we have 0, 12, C2, 6, C2L, 0, minus 12, minus 12, C2, and then 6, C2L. Okay. And so if you notice from the C1, C2, the C1 comes from the truss and the C2 comes from the beam. Okay. Then we have 0, 6, C2L, 4, C2L, 0, minus 6, C2L, and then 2, C2L. We have minus C1, Let's bring that closer here. Minus C1, 0, 0, C1, 0, 0. And then we have 0, minus 12, C2, minus 6, C2L, 0, 12, C2, minus 6, C2L. Right, and then our last column, 0, 6C2L, 2C2L, 0, minus 6C2L, 4C2L squared. Okay. And so this guy right here, this is the element stiffness matrix for a frame in the local coordinates. Okay. And so all we did to get here was we just basically stacked the element stiffness for a truss on top of the element stiffness for a beam. Okay. And so you can see the truss elements here are given by all the C1s. Okay. So all of those came from the truss. Meanwhile, all of these guys right here, let me just box them regularly. All of those guys came from the beam. Okay. And so if you look at just the size of these matrices, so if you look at the magenta terms, that forms our 2x2 element stiffness matrix for the truss. And then the green terms, that's our 4x4 element stiffness for a beam in the local coordinates. Okay. All right, any questions on this? Okay. And so that's a start. So that gives us our element stiffness in the local coordinates. But in order to solve most problems, we need to be able to put this into the stationary coordinates. Okay? And so we're going to follow the exact same process that we did for the beam. And so we're going to pre-multiply by our transformation matrix and then post-multiply by our transformation. Okay? And then we get something really massive. So I'm going to write it down here just for the sake of completion, but I would definitely recommend you just kind of just sit tight and just kind of read the one in the notes, because with this iPad, there's only so much I can do because it's only so small. So I'm going to have to write this on kind of multiple lines, and so you're going to have a much easier time reading the one that's off the lecture notes. So actually, if you want to open that up and then just follow along there and just kind of shout every time I make a mistake, that's you can do that too. But I'm gonna start writing it down. So basically, you know, if we took the matrix that we had in our previous page, our 6x6, and then we pre-multiplied by the transformation matrix transpose, and we post-multiplied by the transformation matrix, we get the following. Okay. All right. So first of all, we have a factor of E over L on the outside. Okay. And then we have the following. Okay. So we have A cosine squared plus 12i all over L squared sine squared. Okay. So that's just the first term. Okay. I don't know why this I keeps being weird. Okay. And so the second term is going to be A minus 12i all over L squared cosine sine. Okay. And then we have minus 6i over L sine. Okay. So just like I predicted, I could only fit half of them. And so let's continue the same thing over here. Okay. So I have a dot, 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 and then dot, dot, dot right here. Right. Then we have minus A times cosine squared plus 12i all over L squared, okay, sine squared. Okay. And then we have a minus A minus 12i all over L squared, cosine sine, and then minus 6i over L sine. Okay. So that's the first row. So thankfully, the first row is the longest because everything else from here has one term less, but it's still going to be massive. So we have a sine squared plus 12i all over L squared, okay, cosine squared. Then we have 6i over L cosine. Okay. Then we have minus a minus 12i all over L squared cosine sine, okay, minus a s squared plus 12i over L squared cosine squared, okay, 6i over L cosine, okay. Maybe I'll just do one more row because it's starting to get old really quickly. And so the third row is going to be 4i, then we have 6i over L, also because I'm going to run out of vertical space here, minus 6i over L cosine, and then 2i. Okay, and this continues on, you know, down for more because this is going to be a 6 by 6 matrix. So you can see it's a lot of stuff. So and so, you know, for your next homework, you know, I'm going to be asking you to do some of these problems. But what I'm going to give you is I'm going to give you a Matlab script that'll automatically compute this for you. Because if you do this by hand, you know, you're literally going to be spending hours, you know, on the homework just inputting numbers into your calculator. And I think that's you know, that's time that could be better spent doing other stuff. So, you know, it's important. You know, the reason we kind of ran through this was just so that you can conceptually see, you know, how we got to this matrix here. But actually doing the computations here, I think is not a good use of time. So, you know, to kind of help you guys out with these problems, I'm going to give you a Matlab script that's just, you know, all you have to do is input the angle and the material properties, so like Young's modulus, area, moment of inertia, and length, and then it'll compute this for you, and you can just write down whatever matrix that comes out. Okay, and so you can see here that, you know, very quickly these problems start to get out of hand, and you really have to start relying on computers in order to capture all of these physics. So finite elements, you know, the way that these classes typically go is that we spend a lot of time in the class developing the theory, but a lot of the computations are usually way too tedious and way too kind of cumbersome to do by hand. And so, you know, we develop the theory, we implement the code, or we apply it in ANSYS, and then we let the computer do most of the work. Okay. All right, any questions on this before we jump into an example? Okay. All right, so let's do an example. Okay, so say that we have a square, right? And so let's say that we have ground that's like this, and then we have a frame, 3 frame elements. Okay. Right. So we'll call this element A, element B, element C. Okay. And so the length here will be 10 feet. Okay. We have a horizontal force here, so this would be 10K pounds. Okay. And then we'll also label all the nodes. We'll call this node 1, node 2, node 3, node 4. Okay. And then we're also going to apply a moment. And so the moment here will be 5,000 pounds inches. Okay. And so if we assume that all elements here are frames, okay. And so from this, let's compute the displacements and the rotations at every node. Okay. And so in order to do that, we need some material properties. So let's go ahead and write those down. So first we have our Young's modulus. And my pencil keeps losing signal. And so our Young's modulus here will be 30 times 10 to the 6 psi. Okay. Next we have our area. So our area is going to be 10 inches squared. Okay. We have a moment of inertia for elements A and B, A and C. Okay, so this would be I1 is equal to 200 into the fourths. So this is for elements A plus C. Okay. And next we have a moment of inertia of 100 inches to the fourth, and this is for element B. Okay. Okay, and so in order to solve for this finite element problem, we're going to follow our same process. So we're going to write down the element stiffness matrices for every element. Okay. And then once we have the element stiffness matrix, we're going to assemble them into the global system, apply boundary conditions, and then solve. Okay. And so the biggest challenge with these frame problems is that your global system and actually all your matrices are going to be enormous. And so, you know, it takes a lot of space to write these guys, but the process is still the same. And so, you know, we're going to go through that right here. Okay. Before we jump into that, are there any questions on the problem setup? Okay. Okay, so let's run through this. Okay. So let's start with element A. So element A, our angle here is 90. Okay. And so cosine of 90 is equal to 0, and sine 90 is equal to 1. Okay. So I chose this as our first example problem on purpose because the fact that we have a 90-degree angle means a ton of terms are going to cancel out. Okay. Right. And so I'm going to give you the Matlab script, but if you did want to compute this by hand, usually it's helpful to compute some of these constants ahead of time. Okay. And so let's say that you want to compute 12I over L squared. Okay. This is going to be 1.67 inches squared. Okay. Next, we can compute 6I over L. And this would be 10 inches cubed. Okay. And then finally, we can compute E over L, which is the term that's out in front. And it's going to be 250,000 pounds per inches cubed. Okay. Okay. And so we plug all these numbers in. You know, for now, we can just assume that Matlab did it. Okay. And then we get the following matrix. So first we have our E over L factor out in front. Okay. And then we have our 6 by 6 matrix here. So it's going to be 0.167, 0, minus 10, negative 0.167, 0, minus 10. Okay. Then we have 0, 10, 0, 0, minus 10, 0. Okay. Then we have minus 10, 0, 800, 10, 0, 400. Okay. Right, then we have minus 0.167, 0, 10, 0.167, 0, 10. Okay. We have 0, minus 10, 0, 0, 10, 0. Then we have minus 10, 0, 400, 10, 0, 800. Okay. And so when they're all numbers like that, it barely fits. Okay.
Professor Tran?
Yep.
So The way you got that matrix was using the frames element stiffness matrix that you did in the note before you drew the example, correct?
That's correct. Yeah. So that's that massive thing that I started writing here, but I ran out of room. But it's in the notes. So I basically plugged in everything for like the areas and the L's and the I's and all the sines and cosines here. So you know, doing this by hand, you know, that's a little bit too unreasonable. I'm not that cruel. And so I'm going to give you guys a Matlab script to basically compute this for you. So all you have to do for the Matlab script, you have to input the angle, input all the material properties, and it'll give you the 6x6 matrix for you like that. So hopefully that should save you guys a lot of time. And so so I'll post that along with the second homework, which is probably going to come out end of this week. Okay, and so we also have to note which nodes that this guy works on. Okay, and so this works on nodes 1 and 2. Okay. All right. Any questions on this? Okay. Okay. So then let's do element B. Right. And so element B, we have theta is equal to 0 in this case. Okay. And then if we compute the constants, we have 12I over L squared. This is 0.00 or 0.0835 inches squared. 6I over L is 5 inches cubed, right? And then E over L is still the same. This is 250 pounds per inches cubed. Okay. And so we can plug this guy in and get this a similar kind of matrix. So we have KB. So I'll just write the first 3 rows, and then you can kind of pick it up from there. So this is going to be 250,000. Okay. 10, 0, 0, minus 10, 0, 0. Okay. Then we have 0, 0.0835, 5, 0, minus 0.0835, and then 5. You guys hear my cat in the background? 0, 5, 400, 0, minus 5, 200. Okay. And then, you know, there's 3 more rows here, but you get the idea. So this is just kind of just a plug and chug at this point. Okay. And then we can do the same for element C. Okay. And so element C, you know, because the lower number node is on top, and then so in order to rotate all around, so our theta has to be 270 degrees. Okay. And so these actually have the same parameters as element A, and so just the sum of the signs would be reversed. And so KC will also equal 250K, and then we'll have our 6x6 matrix right here. Okay. And so again, you know, I have all these written out in the notes. It's just in the lecture, you know, just because my iPad's really small and you know we only have a limited amount of time, I'll leave that to you guys. But it's basically just the same process we did before. It's just the matrix is just a lot bigger. Okay. Okay. And so now that we have the element stiffness matrices, well, you know, you have them in the notes. What we're going to do is now we're going to assemble our global system. Okay. And since we have 4 different nodes here, and each of the nodes has 3 different degrees of freedom, that means our global system is going to be 12 by 12. Okay. And so, you know, the global system I'm also not going to write because I'm definitely not going to be able to fit it. But I'll at least show you kind of, you know, where each of the stuff fits into the matrix. Okay. All right. Any questions on this? Okay. Okay. And so let's write out our global system. Well, I'll give you the bones of it. Okay. And so you can imagine this is a 12 by 12 matrix, okay, which is way too big to fit here. But what we can do at least is I can tell you, where each of the different element stiffness matrices fit in. Okay. And so first we have element A, and so this is our 6 by 6 matrix from element A. Next, we have the 6 by 6 matrix from element B. Okay. And then finally, we have the 6 by 6 matrix from element C. Okay. And so these are all the the same methods that we used before. It's just now we've upped the scale quite a bit because we've added rotations and transverse displacements. Okay. And so I made a note of this in the homework too. The homework's not posted yet, but it will be posted soon. That to construct this global system here, I don't want you guys to have to write down such a long big matrix, because it's some of the homework problems actually are going to get even bigger than this. And so if you want to use like a spreadsheet program like Microsoft Excel or Google Sheets to kind of present the global stiffness in kind of a neat way, I would go ahead and use that, because that's kind of a lot more practical. Okay. And so let's say that we apply this matrix, and then we apply our boundary conditions. But we haven't said where our boundary conditions are yet. And so our boundary conditions from the original problem stated that nodes 1 and 4 are fixed. Okay. And so nodes 1 and 4, that means it's going to knock out the first 3 rows of the matrix. So you have u1y is equal to u1x, which is equal to theta 1 is equal to 0. Okay. And then also we have the same for u4. So u4x is equal to u4y is equal to theta 4. This is equal to 0. Okay. And so that means that the first 3 rows of this matrix and then also the last 3 rows, okay, those are going to be replaced with our Dirichlet boundary condition. So we're going to put 1 on the diagonal and zeros everywhere else. And then, zeros on the right-hand side. And then also we have to put our modes on the right-hand side too. So remember, we had 2 modes in this case. We had a mode of 10,000 on U2x. And we also have a moment of 5,000 on theta 3. Okay. So I know, I'm skipping all the numbers here, but all the numbers are given in the lecture notes. But are there any questions on this? Okay. Okay. And so once you plug that in, you can solve for the solution, and and you'll get all the deformations, all the displacements, all the rotations at every node that can do it in this mesh. So in this case, it's only been nodes 2 and 3, and so you're going to have 6 non-zero values. Okay. Okay. And so before we move on to the next example, I just want to make a couple quick notes. And so first of all, just like we did in the beam equation, what you can do here is you can compute the reaction forces on each of the elements, okay, or each of the nodes. Okay. And we're going to do this in the exact same way. So the way that we did this was we took our deformation solution. Okay. And then we multiplied this by our element stiffness matrix that we had before we applied our boundary conditions. Okay. or not element stiffness matrix, sorry, the global stiffness matrix. Okay, and so that'll give you the all of the reaction forces and reaction moments in the stationary coordinates. Okay, and so one thing that we haven't done yet is take these reaction forces and then transform them back into the local system. Okay. And so why would you want to do this? So, oftentimes what's useful is to compute this, the forces down the length of the element and transverse the element, because from those things you can compute things like the stresses or like the bending stresses. Okay. And when the forces and the moments are in the stationary system, then you can't do this. So in order to get the like the stresses, usually it's a good idea to transform this back into the local system. Okay. And the way that you do that is you just apply the same transformation matrix that we've seen before. Okay. Okay. And so let's go ahead and just show what that is. Okay. And so first on the left-hand side here, I have all the local forces. So all these guys are going to have a hat. Okay. So you have F1x hat, F1y hat, M1 hat, F2x hat, F2y hat, and M2 hat. Okay. And this is going to be equal to our transformation matrix, okay, our 6x6 version. And so this is going to be cosine, sine, minus sine, or minus sine, sorry. Cosine, minus sine, cosine, 1, okay, and then a bunch of zeros. Okay, and then the same thing down here. So we have cosine, minus sine, 0, minus sine, cosine, 0. Actually, I think this should be positive sine. I think it was a typo in my notes. Yeah. And then 0, 0, 1. Okay. And on the right here, we have the global reaction forces. So we have F1x without the hat, F1y, M1, F2x, F2y, M2. Okay. And so all we have to do is perform this matrix multiplication, and then we get the reaction forces in the local system to the element. Okay. And then from there, we can compute things like stresses that are either down the length of the element or from bending. Okay. All right. Any questions on this? Okay. And so let me start our next example, because and this example kind of ties in what we did at the beginning today, and it's a problem with the frame but with some distributed loading. Okay. Okay. And so for this problem, we have a frame element that looks like this. So thankfully, we only have 2 elements in this case. Okay. Right. We'll call this element A. We'll call this element B. Okay. This angle right here is 45 degrees. Okay. Okay, and we'll label the nodes just like that. Okay. And then up top right here, we're going to have a distributed loading on element B. Okay. And then the function for this, we'll say Wx is simply equal to 1,000 pounds per feet. Okay. And so it's just a constant distributed loading. So it's not like the ramp that we saw before. Okay. Okay, so just like the previous problem, we're interested in solving for the for all the displacements here. Okay. Let's add some additional parameters. And so we know the length of this element here is 40 feet. Okay. And we also know that the horizontal length here is 30 feet. Okay. We have the Young's modulus. So the Young's modulus is going to be 30 times 10 to the 6 psi. Okay. A, which is 100 inches squared. Okay. I, which is 1,000 inches to the 4th. And so this is going to apply for all the elements in our system. Okay. And then what we're going to do is we're going to solve for the displacements. Okay. And since the system is fixed at nodes 1 and 3, the only displacements that we can actually solve for are at node 2. Okay. Okay. And so we have here another frame problem. So we can follow the same process that we did before. The big difference here is that we have this distributed loading. Okay. And so before we actually do anything, the first thing that we have to do is we have to convert this distributed loading into the equivalent nodal loads. Okay. Okay, so let's go ahead and do that. Okay. And so to do this, remember the principle that we're going to apply here is the principle of equivalent work. Okay. And so what that states is that the integral from 0 to L of our distributed load multiplied by our displacement function uy of x, okay, dx. Okay, this has to be equal to the following. So this is f1y u1y plus m1 theta 1 plus f2y u2y plus m2 theta 2. Okay. And so this quantity on the left-hand side here, this is the work done by the distributed load. Okay, so this is work distribute. And then this over here, this is the work done by the nodal loads. Okay, so this is work discrete. Okay. And so, most of the work in this problem is going to be evaluating this integral on the right here, on the left. Okay. So thankfully, this integral is going to be a little bit easier to evaluate, just by a smidge, than the one we did as an example at the end of last class. And the reason is because our w of x here is a constant function. And so that's going to simplify our integrals very, very slightly, but it's still going to be quite a bit of terms. Okay. All right, any questions on the problem setup? Okay. And so let's start integrating. Okay. And so let's kind of remind ourselves what uy is. Okay. So remember, uy is a function that describes how the transverse displacement of this frame varies as a function of x. Okay. And so this function is given by 2 all over L cubed u1y minus u2y, okay, plus 1 over L squared theta 1 plus theta 2, okay, and this is all multiplied by x cubed. Okay? And so remember, because we derived this equation from the beam equations, And since the beam equation was a fourth order differential equation, we use a cubic function here. So that's why we have x cubed, okay, plus minus 3 all over L squared times u1y minus u2y, okay, minus 1 over L 2 theta 1 plus theta 2, okay, and that's all multiplied by x squared, okay, and it's going to be multiplied by theta 1x plus u1y, okay. Okay, and so what we need to do here is, because since our w of x here is just a constant, what we can do is we can just simply start integrating this guy. Okay? Since our so if our w of x depended on x, we would have to account for that x dependence here. But since that's not the case, our w of x is just a constant. We can just start multiplying or integrating. Okay. Okay. And so we can say that our work distribute is equal to, and so since our w is just a constant, we're going to pull that out. So we have 1,000 out here. Okay, so that was the value of our w of x, right? And then to this, we're going to start integrating all the other terms. Okay. All right, so let's start with the first one. So first we have 2 over L cubed times u1y minus u2y plus 1 over L squared theta 1 plus theta 2. Okay. And the integral of x cubed is going to be x to the 4th, all divided by 4. Okay. Plus 3 minus 3 over L squared times u1y minus u2y minus 1 over L 2 theta 1 plus theta 2. Okay. And then the integral of x squared, which is x cubed over 3. Okay. All right. Then we have plus the integral of theta 1x, which is theta 1 x squared over 2. Okay. And then plus integral of u1y, which is u1 y x. Okay. And then all this is going to be evaluated from 0 to L. Okay. Where L in this case, I think, is going to be 40 feet. Okay. Right. Oh, sorry. And since this distributed force is going down, we have a minus 1,000 here. Right. All right. So the next step is we're basically going to start evaluating this at the integration bounds. Okay. All right. So I know it's a lot, so I'm going to give people a chance just to write this down. But while people are writing it down, are there any questions on this? Okay. Do people still need a couple minutes? This is all in the notes too, so you can definitely cross-reference with that as well. Yeah, it's probably a lot. It's definitely a lot neater there than it is here. That's for sure. Okay. And so let's start evaluating the integrals. And so if we do that, we get the following. Okay. So we have a minus 1,000 out in front. Okay. Then we have L over 2. And that's multiplied by u1y minus u2y. Okay. Plus L squared over 4, theta 1 plus theta 2. Okay. And so I evaluated the x at x is equal to L, and I distributed that through. So that's how I got this. Okay. Minus L times u1y minus u2y, okay, minus L squared over 3 times 2 theta 1 plus theta 2, okay, plus theta 1 L squared over 2 plus u1y L. Okay, and so now what we can do is we can just plug in for L. Okay, and then let's distribute the minus 1002. Okay, and then we end up with the following. Okay, and so we get 2 e to the 4, and so that's 20,000 minus 20,000, sorry, times u1y minus u2y minus 4e to the 5th, okay, times theta 1 plus theta 2 plus 4e4 times u1y minus u2y, okay, plus 5.33 e5 times 2 theta 1 plus theta 2, okay, minus 8 e5 times theta 1, okay, minus 4 e4 u1y, okay. And so just like we did before, we're going to sort this into the coefficients for the different terms. Okay. Okay. We're going to leave off on the exact same spot that we kind of left off last time, but with a different example. Okay, any questions on this? And so after we sort the coefficients and then we add them all up together, then we end up with the following, okay? And so we get minus, and we'll use colors here, minus 2 e4 u1y, okay, minus 1.33 e5 theta 1, okay. So next we have minus 2 e4 u2y, and then finally we have a positive 1.33 e5 theta 2, okay. And so from this we can see that we have f1y is equal to minus 2 e4, okay, pounds in this case, okay. We have m1 is equal to minus 1.33 e5, okay, pounds feet. We have f2y is equal to minus 2 e4 pounds, and then we have m3 or m2 equal to a positive 1.33 e5 pounds feet. Okay, so just like we did before, just reading off the coefficients, you know, for this problem. Okay. Okay, and so now that we've done that, we have all the nodal nodes, okay? And we can apply this onto our problem to, in order to do the finite elements, okay? And so just kind of a quick sanity check, you know, we noticed that we have a constant distributed load, and we see that our F2y and F1y, they have the same magnitude, and so that kind of makes sense because it's a load that's evenly distributed. So, you know, just kind of small sanity checks like that can help you out big, okay? Oh, Chris, we can talk about that after the lecture if you want, okay? Okay, and so when we pick this up on Monday, we'll finish up this example, and then we'll see, you know, how do we deal with these, you know, kinds of situations, okay? So are there any kind of final questions on today's lecture?
I have a question, Professor.
Sure, what's up?
The L here is the distance between the node 2 and 3, that's right?
Yes, yeah. So it's the, so since this distributed load was only on element B right here, the L that we use is the length for element B. So that's going to be 40 feet.
Okay, thank you.
Mm-hmm. All right. All right, so if there's no more questions, then I'll sign off for this week. I haven't put the minute paper up for this week, but it'll be up in 5 minutes right after the lecture. So if not, you know, I hope you guys have a great weekend. Thanks again for tuning in, and I'll see you guys on Monday. Thanks, guys. I think I'm okay. I think just the core ops, if you can find it. Thank you. Okay. All right, Chris, so what was your question about the for loop, or can a loop condition read what? Usually to find an even number, you just have to just do the mod. So you can just do mod I and then comma 2. And then if that's equal to 0, so because every even number you divide by 2, you get, oh, actually, hang on. Wait, so you mod 2. Actually, yeah, you mod 2 every time, because if you divide by an even number, then you shouldn't get any remainder. So if your mod number comma 2 is, if it's 0, then it's an even number, but if it's 1, then it's an odd number. Yeah. Right, exactly. Mm-hmm.